It is now my pleasure to introduce Liliane Maia from Universidade de Brasilia. And she's going to talk us about new results on nonlinear Shocard equation with symmetry. Thank you very much, Liliane, for being here, for accepting our invitation, and please go on.
Thank you very much, Alberto and Monica. I'm going to speak in English because I'm already crazy about Portuguese, Italian, and Spanish. So let me go more secure to this. So thank you very much for the invitation to be here with Benedetta, with Monica in Mexico. This is my first trip after all this pandemic time to work, so I'm really happy to be here and I'm enjoying it a lot. So I'm going to talk about this work with Benedetta and Delia Esquerra from Lisbon now. She's from Italy, but now she works in Lisbon. And on things that we have learned from Monica, with symmetry. Monica. So let me see what I can tell you this morning. Bene? Come va? Okay. Okay, so here Shocard equation with a p power. So it's the linear part minus Laplacian of u plus I'm going to talk about this work with the potential v of x. It's not autonomous, the whole problem. Alpha is the Higgs potential, Higgs kernel, and u to the p, and then everything is going to depend on this power p. So we talk about n greater or equal to 2. I alpha is the Ritz operator that is shown here with this x to the n minus alpha in the denominator, and then immediately arises this question on where can we work, where can p travel, let's say, exist. So we get this lower, I think they call it lower critical power and upper critical power, isn't it, Monica? I don't. But anyways, P has to be in this range in order to have the functional well-defined and to work with the functional associated to these equations. The whole thing is to exploit the V of X potential and see where it can, what kind of potential we can have for this kind of problem. So we chose a problem with V of X potential that goes to a positive limit at infinity. And just recovering some aspects of this kind of study, why you study this equation. It's classical now, the physical model, which comes from Froelich and Pecars in 37, 54. They modeled the Polaron and condensed matter physics with this kind of non-local term to describe how the electrons behave when they model this physical problem. Then Shocard in 76 introduced the modeling of one component plasma, also used to this equation with I2, alpha equals to 2 and P equals to 2. Lieb and Thomas, 76 and 97, studied exact ground state solutions for modeling strong coupling polarons, and many others, okay, closer to us, that have approached this just a basic model. The Shocard equation comes with this non-local interaction, non-local term, which is the convolution term, and we look for standing waves. And when looking for standing waves, we end up with the elliptic equation. Focusing. In our setting, let's say for P different from 2 and alpha different from 2, from just the physical model, many others have faced and approached the problem, like Lieb, Lyons, and then there is this work, Moros van Schachten, which is very interesting to read because they do a review on the literature and the kind of problems that have been solved for the Shocard equation. But going on with our questions with the V of X variable of this potential, first of all, we have to see that for P in this range, okay, this convolution term is well defined and is a finite integral if and only if P is in this range. And this comes from Hardy-Littlewood-Sobolev inequality. So in order to try to find a critical point for this functional in H1, we have to live in this range of P, if and only if. And then this is well defined, and this term is the norm and the linear term, and we can try to find critical points for this function. Okay, if V of X is below the limit at infinity, this has been one of the first interesting papers, or fundamental papers in the Shocard equation for using the elliptic approach, variational approach by Pierre-Louis Lyon in '84. And basically, if V is from below, you have concentration compactness, and then you find a solution for the problem with a variable potential. But in our case, we were curious to know what happens if V approaches from above and below. Not from below, which is the case of Pierre-Louis Lyon, but for example, on oscillating potential like this. And this has to do in some sense with the physics too, because it depends on the material and depends on the distribution of electrons. So it's not that you have a very regular lattice of material and distribution of electrons. So V of X approaches V from above or oscillating, higher action level solutions have to be searched. This requires a deep study of the possible lack of compactness for a bounded Palais-Mail sequence due to the problem in Rn. Okay. So let's see what is the idea here. We search for bound states, not for ground states. For example, when V comes from above, you're not going to attain the ground state. So you have to look for solutions in higher level energies. And this is going to require some idea of this concentration compactness, or the version of the splitting lemma by Struve, for example. The immediately furnishes compactness of quantized energy intervals whenever the so-called problem at infinity has a positive ground state solution. So as it is for the Schrödinger equation, for example, focusing Schrödinger, we have to tackle, or we have to exploit the information on the limit problem, which we call the limit problem, that has a V constant potential here. But how much do we know about the solution of this type of problem? Okay, existence of positive solution for the autonomous problem goes back to Lieb and Lyons, and these results have been extended by Moroz van Schaftingen for other P's. Okay, for P equals to 2, Lieb and Lyons and others. The autonomous problem has a positive radially symmetric least action solution for any P in that range of Hardy-Littlewood-Sobolev inequality. Anyways, this is going to be fundamental in order to create a solution for our variable potential problem, okay? So we really use the least action solution, and we really depends on how, okay, the qualitative properties, positivity, radially symmetric, and decays. We're going to see it. And what about uniqueness? Because in order to face this problem with no hypothesis of symmetry, we really end up at some uniqueness demand, let's say. We have to know about uniqueness of the limit problem, the solution, positive solution of the limit problem. And this is very little is known about the uniqueness properties. It's a big open problem for Shocard. There are informations on P equals to 2, alpha equals to 2, which is the classical physical problem. and n 3, 4, or 5. So with a variable potential, we were able to use uniqueness and no symmetry in order to prove some results of existence of bound state solutions. This is another work that I'm not going to talk today, but it's a work with Benedetta and Dario last year too. Okay, so if we don't have uniqueness, since it's not well known for other P's and other alphas, we have to try other resources, let's say. And then we tried the symmetry approach. We have symmetric properties. We assume symmetric properties on the potential. We find critical values of the functional with symmetry, with in spaces with symmetry, and then we minimize IV on a symmetric Nehari manifold. So that's pretty much the sketch that Monica and so many others have used. So this is the path we decided to take when we don't have symmetry, we don't have uniqueness. Symmetry is going to increase the least action level, allowing to construct a last-Mail sequence in which is not a minimizing sequence, okay? A symmetric minimizing level lies in the range where compactness properties hold. So that's what we exploit. If we are in a symmetric setting, where can we be sure that we have compactness in order to take the Pellaci sequence and limit and the candidate for the solution? So that's what we managed. So think about symmetric potentials. A good candidate is made of translations. Okay, if we are assuming, for example, the 3 symmetry in the sphere, okay? So we're going, the idea is to put one bump of a ground state solution for the limit problem in each stop of this orbit, let's say, oops, here, here, and here, and then move these bumps very far away in order to construct a suitable PS sequence, let's say, candidate. But then this all this idea is going to depend on the interaction of these bumps, and that's what we exploit, and the behavior of this interaction with respect to the P power of the Shocard equation. So let's see how it goes. Functional decay properties of the ground state solution, positive ground states are required in order to study these interactions. The nonlinear Schrödinger equation, this exponential decay of W plays a crucial role. But here depends on the P, the decay that we have. So first of all, we have to deal with these differences in decay. In the case of the autonomous Shocard, it depends on the P, that's what I said. If P is greater or equal to 2, the positive solution decays exponentially. And this was very well said and shown, worked with by Klepp and Salazar in their work of 2013, in order to find symmetric solutions for the Shocard equation. But then when P is less than 2, one sees that the real non-locality feature of the autonomous Shocard, because the nonlinearity in this case is not focusing enough and the decay of W is not exponential, then you have to consider the convolution term is going to spread out the influence of one bump over the other. And that's what we realized when we studied the P less than 2 case, because of the polynomial type of decay that the ground state has. So let's see. So we approach the problem with symmetric groups. We have finite least orbits. Let's see. So if you take G, a closed subgroup of linear isometries in Rn, and we take LG, the minimum cardinality of a point X by the action G. And this we are supposing or assuming finite. So the orbit of the point, or at least the minimum orbit, is going to have a finite number of stops. That's the type of subgroup that we used. So the cardinality of G of X is this representation, and in our case, the L of G's are finite. So we have a finite number of stops in the minimum orbit. Then we have the G invariant set sigma, which are the points of the sphere Sn minus 2 minus 1 that have this cardinality in the orbit, the minimum cardinality, let's say. And for our approach, we're going to need basically this, the mg number, which is the infimum of mg's on orbits G of Z, Z in the sphere. And what is the mu G of Z? Is the distance between the stops of the orbit, the minimum distance between the stops of the orbit. If the cardinality is bigger than 2, and 2z, which is the distance 2, if the cardinality is 1. So hopefully this is clear, because Monica is an expert, probably has taught all of us has taught me and has taught everybody. Yeah, you see that? Okay, so the first result is for p less than 2, which is, I think, the more surprising one, is if you take LG, a closed subgroup with the minimum orbit with size, or with the stops bigger or equal to 2 stops, and assume the exponent p is below 2 and above the lower critical, and the potential has a limit v infinity and goes to this limit in this rational way. Let's see, power decay. Okay, for some beta, this is not clear, depends on the proof, but for some beta, I don't know if you see here, n minus alpha over 2 minus p, then v, if, okay, the problem is symmetric. So if V is G invariant, then the problem has a positive G invariant solution. So this was the first result for P less than 2. When P is less than 2, different phenomena compared to Schrödinger equation appears in studying the nonlinearity involving the convolutional term. So we are going to see, indeed, the effect of the nonlinearity are spread in a less concentrated region, so the interactions between two different translations of omega becomes relevant even in the centers of translations, even if the centers are far away from each other. So we're going to see how this spread interaction occurs. Phenomena due to polynomial decay of value is resembling to that which occur in the context of non-local operators like fractional Laplacian. Okay, for p bigger than 2, or p equals to 2 and alpha less than equals to n minus 1, it is going to, okay, the potential that we have to, or decays on the potential are going to depend on some exponential decay too. Why? Because the ground state solution has a polynomial decay and has an exponential decay, and this is going to affect the estimates in the whole problem. So here, for LG bigger or equal to 2 and P in the range where the function is well defined, and for P equals to 2, for example, in alpha less than n minus 1, okay, we suppose that the potential V decays with this polynomial part and exponential part. Okay, how? The exponential part, if the potential is going to be, okay, decay faster than the distance, the minimum distance between the, or in the orbits of the point, okay? The points, the mu g is the minimum distance. So if you have a decay which is faster, be bigger than this, then for any power here, doesn't matter, just the exponential part takes over. But if you are exactly at the decay of the ground state solution, then the potential, the power here is going to take place, okay? So the interaction is going to be good when we estimate the interactions. If you have a V that decays with a small power, let's say, with respect to the rational part, okay? So we can assume V with exponential decay exactly as 2 times the decay of the ground state solution, but then you have to change a little bit or consider the polynomial part. So that's what we find for P bigger and equal to 2. Doesn't matter here, okay? This is technical. I should, but then depending on these nu and anyways, this appears because of the decay of the Shocard ground state solution. But then V is G, if V is G invariant, the problem has a positive G invariant solution. So this is a second result for P is bigger than 2. I'm going to say later, but in advance here, the LG that Monica and Dora worked were bigger or equal to 3. So we were able to decrease this a little bit. And that's the effect. Powers P and decay. The effect of the convolution term is going to be felt depending on P bigger than 2 or equal, bigger and equal to 2 or less than 2. The different behaviors, I have talked about this already. So it differs with the Schrodinger equation because we can have P is less than 2 here. When P is less than 2, the role of the convolution and then the polynomial part takes, let's say, importance. Okay, we are looking for bound state positive solutions, okay? And depending on how V of X approaches the infinity from above, we have to go into this higher level energies. I said uniqueness is not known, so this is a challenge when you face Shocard equation. And Palais-Mayo and compactness properties depending on the asymptotic decay of the potential V in order to get recover compactness. But let me go faster. Okay, the case of LG is equal to plus infinity, we have not touched, but it was already approached when the infimum of V is bigger than 0 by Cingolani-Klebsecki for P in the whole range. P from lower critical to upper critical. So they have answered for the existence of positive solutions when LG is infinity. In our case, LG is finite, so it's complementary to this. And in Klebs-Salazar, as I said, the problem was approached for P equals to or equals bigger or equal to 2, for LG bigger or equal to 3. And we were able to improve this a little bit, having just 2 stops in our orbit, okay? But let me go faster. How does it go, Penny? Okay. Okay. This is another theorem that we had to be more careful when P is exactly 2 and alpha is in this range. The problem here is that the decay of the ground state solution is not only an exponential linear decay, but has another power in the exponential term. So this brings other difficulties to estimating the problem. Okay, for B equals to the range, which is the decay of the ground state, and for B equal. So we had to face, when interacting different bumps, let's say, we had to be more delicate in the study of this term. So it's not just e to the minus beta x, but it's e to the minus beta x plus t prime x to the gamma prime. So this was another contribution in this type of works that we, in these works that we did. Then V, if V is G invariant, we were still able to find the G invariant positive solution for the problem with a variable potential. Oops, no, Benny. Okay, so let me give an idea, very summarized idea, because I think most of you know this kind of approach. We try to minimize the functional with G symmetry, okay, on this Nehari's manifold or set, where the candidates for critical points are. So this is the Nehari symmetric, the infimum on the Nehari symmetric for the functional, and this is the Nehari equation. When P is greater or equal to 2, the functional is twice differentiable. So we can deal over deformations and everything on the Nehari manifold. But if P is less than 2, it's not so. So the first thing we have to be careful is to go into a setting where you can do deformation, because you have some non-smoothness of the Nehari manifold set. So we had to do this, but I'm not going to, it's just to call the attention for someone that is reading the paper, why are they doing this now? It's because for P less than 2, you have to be more careful about the deformations and everything. And this is the functional associated to the limit problem with V infinity here, and you also have the Nehari structure and the infimum on this. So all the challenges to compare the levels here with the levels with the V variable potential. Not anything surprising because it's being used. Okay, so in order to do this kind of approaches, you have to study very carefully the interactions, and then you have to know well the decay of the solutions. And this is a work of Moritz van Schattingen on finding exact decay for the ground state solutions. When P is less than 2, the ground state decays as a power. And when P is bigger than 2 or equal to 2, it comes the exponential term, which gives different kinds of estimates. In this case, P is equal to 2, or and alpha is in this range, the exponential term is like the Schrödinger decay. So in some sense, it's easier because we know how to deal with these Schrödinger solutions. But when P is equal to 2 and alpha is in this range for the convolution term, then the decay of the ground state is exponential plus another power of x. And this introduces more delicate estimates. That's the, so everything comes from really from the decays, different decays of the ground states on ranges of P's and alphas for the Shocard equation. Okay, the idea, take an orbit, put a bump in each stop of the orbit and take it very far away and see if we can construct let's say a PS sequence with this kind of some construction of bumps, okay, which is in the range of the estimation. So this is it. Here GI are the stops of the zeta in the Sn-1 sphere in Rn. And then far away from the origin, you're going to put a bump of ground state solution, positive ground state. And then everything depends on this, which we call epsilon rij, which is the interaction of bumps. The convolution term at one point I, and at the j point. So this is the term that is going to, let's say, put light where these things are really interacting and bringing to the problem some information. So this is it, but since we are in the Shocard equation, this means that you are testing with function wj, and because you have different points in this orbit and it stops, you have a sum of these epsilon r ij terms. This is the sum of the bumps, and you do this up to the last stop, okay? So this is the construction in order to get a correct or a good PS sequence. But anyway, what do we do when we analyze the interaction of all these bumps, which are very far away? If p is less than 2 and bigger than this critical lower power, the epsilon ijr terms, which measures the interaction of two different bumps in I and in J stop, they are a power interaction, and that's the power, the exponent of the power n minus alpha 2 minus p interaction, okay? So there is no exponential, and then I say this here, because there is no exponential term, and in the exponential term is where you see the distance between the points. Here, the distance between the points is not going to count or bring any information to estimate in these very interactions. So that's what I say here. For p less than 2, the distance dij does not come into play between any 2 points. So this marks a big difference between this problem for p less than 2 or for p bigger and equals to 2. For example, in the approach of Salazar, you have to study this distance and to be very precise about how they come into the estimates. Here, no, just the power of R is going to, let's say, bring some information to the problem. So if P is less than 2, our hypothesis on the potential is with a power decay for power beta bigger than n minus alpha 2 minus P, which is the epsilon IJR decay. So if you are decaying faster but polynomial with respect to R, this term is going to be small order of those epsilon R terms. So that's the type of hypothesis we need in this case. Because you have many stops, Ij stops, you have to see how they are interacting, and all the interactions are important because of the convolution term. And that's what we realized when doing the estimates. And basically, I'm going to give a picture, so it's very technical, the kind of interactions it happens. But what happens differently from the Schrödinger equation is if you have a bump here and a bump here in the Schrödinger equation, basically this square and this square were important. The only parts that the interaction was very, had the important power. But now with the convolution term, what happens is, for example, a bump in this center influences all this region. All this has to count. And that's what we thought we called the non-local importance of the convolution term. So what we calculated is that the influence of a bump here is felt in the whole L region and not only in this other square. But anyways, these are estimates, technical, it's all done in the work, but we end up, when we try to see what is the nonlinear I alpha convolution sum of different bumps of power p to the power p, when we estimate this is going to be pieces in each bump, which is going to help us see how many copies of energies we have. And then because of that non-local interaction, we have P times epsilon R, and also a sum of this L influence that I put it here. Okay. I'm not going to give the details, but basically the difference is when you are studying Schrödinger equation, local Schrödinger, basically what you see is this P times epsilon R. And in our approach with the convolution terms, the L terms appear here. So we have this plus this to estimate. And then what do? We take this sum of a finite number of bumps, okay? There is a T that projects in the Nehari manifold with symmetry G. The projection is unique as usually. Then we have a CG VU, which is V, which is the infimum on Nehari, and it's strictly positive. But then we had to do some, because P is less than 2, we had to do some topological let's say, the homeomorphism with the sphere, go to the sphere, come back to the Nehari, because the Nehari is not C2, whatever. But this is just a complement. The action level now, how do we estimate the action level? When you project the sum of bumps and you calculate the energy, the action level there, what we find is we find LG copies of the energy because we have LG bumps. And then we have this sum which comes from those L influences, okay? And small order terms. So basically, this component here is coming not only from the influence of a bump to another, but also in the L influence of the polynomial decay. Anyways, when you plug this into the expression of IV, okay, and the LG C infinity G estimate, what we get is basically, I'm just putting some information here on how to get to that expression, but basically it's LG copies of the energy of one bump minus something which comes from those L interactions. Since this is a term with finite, it's a finite number, okay? You're subtracting from LG, C infinity, and this is a small order term, we end up below the LG, G infinity, G energy. And if you are below, you have Pellaci-Mail, and then you take limits. That's how it goes. The end of the proof is this. You have, if you are below, you have a Pellaci-Mail condition by Cingolani-Clepseki. Then you pass to the limit, you get to U in the symmetric space and the symmetric Nehari. The modulus of U is also there. And then we end up coming back by Zucking-Weth argument of homeomorphism with the sphere and getting a solution for the problem for P less than 2. I think my time is finished.
You have 3 minutes.
Okay, just 3 minutes. Just an idea of the other part that was interesting, because many things are also similar, but the region where P greater or equal to 2 and the decay of the ground state has the exponential part with beta minus bx plus something. In order to see the interaction of bumps, we had to confront these terms. And then we had to prove what kind of decay a translated function of this kind of decay in a V decay like this have. And we were able to show that it's, depending on the translation you have, it's the C to the A power and an exponential power with a linear term minus BC plus something else. And this something else comes with all the other informations that we didn't have in the Schrödinger. So we had to prove a lemma like this, which is similar to the lemma of Ambrosetti, Colorado, Ruiz for not with C0. And this helps us estimate interactions when P is greater than 2. But I'm not going to this. Anyways, here is the kind of epsilon r term, which shows the interaction. The interaction has a power of r term plus exponential sum of terms. And this makes things more difficult to estimate. So it's not just an exponential, but the exponential has a minus and a plus. And depending on this, you have to estimate and get the correct, let's say, weight of epsilon r. And then all the work is also to see that this difference, okay, the V of X difference with decay interacts with copies of the bumps as a small order because of the assumptions you made. And then this term is going not to influence the energy. The energy, this does not make the energy higher but lower depending on the sign of the epsilon r term. Let me skip because this is all calculations. You end up with those precise numbers, getting that CVG is less than LG C infinity, and then you are in the Palais-Mayo range and test the limit. Well, thank you very much for the attention.
Thank you, Liliane, for the very nice talk. Are there questions for Liliane?
You all know this better than me.
Well, I have a couple of questions. So you mentioned several times that uniqueness is open. So this means that there is no case where you would have multiplicity of positive solutions in any situation that you know of. Uniqueness is not known and multiplicity is not known in any particular case.
Uniqueness we know for P2, which is the physical classical case. P2, alpha 2, and n equals to 3, 4, and 5.
Okay.
But it's a very interesting open question right now, things on uniqueness of Shogart. I have seen talks recently on the extremes, like for upper and lower critical P's, some results on uniqueness, but I don't know exactly, but in the middle, in the range of P's, bigger than 2, for example, or less than 2, not known, as far as I know.
And can you use similar techniques to construct also sign-changing solutions?
Probably, but there is a result of Gimenti van Schaftingen journal functional analysis, 2 bumps or a sign change which is up and down, okay, that we saw very recently, and it's for P in the whole range, P from lower critical to upper.
Okay.
But it's not for a variable V potential,
Ah,
just for the autonomous problem.
okay.
They proved that.
Well, thank you. Are there any other questions for Liliane? Well, if that's not the case, then we thank again Liliane, we thank again Benedetta. Thank you very much for your very nice talk. And with this, we close our SEDNOL for this semester. Have a good holidays, relax a bit, and we see in the next semester in August. So,
Thanks.
goodbye.
Yes.